Hello everyone, and in this video we're talking about inertia and momentum. Two words which get used interchangeably in everyday language quite often, but they are different according to physics. When something gets moving, it sometimes can't be stopped. Wise words. Well, let's define the quantities to start with. Large objects are hard to move. You might have noticed this, and so the reason for this is because of their mass. A lot of mass is hard to move, and we call the quality of being hard to move inertia. So inertia is the resistance of any object to having its movement altered. That's a more formal way of putting it. So in this sense, you could say it's a reflection of which law of motion. Thinking back to the connection between inertia and mass, you might think that it is the second law of motion. Now let's talk about momentum. If an object is already moving, is there some number we can ascribe to the amount of movement there is? And when I say the amount of movement, that's taking into account the size of the object as well. So if there's a small thing moving very fast, there might be less movement there than a large thing moving very slowly. So then momentum is a quality of moving objects, and we define it as the product of mass and speed. And so if we say it's a product of mass and speed, we already have definitions of those quantities. And this is our momentum equation, P equals mv. So before I show you, I would just ask you, what are the units of momentum? So pause the video if you'd like to, but I'm going to tell you now that it's the kilogram meter per second. Kilogram meter per second is the unit of momentum, and it's not a very convenient unit, but we don't use it terribly often. And it's formed because the quantity is the product of mass in kilograms and speed or velocity in meters per second. So now to draw the distinction between the two, if you haven't already picked up on it, inertia is a quality of mass, and so the more mass something has, the harder it is to change the motion, so the more inertia it has. And so we talk about it in a quantitative way, but we never actually will calculate inertia as a separate quantity of mass, although inertial mass is a very important factor in relativistic physics, which is the physics of fast moving objects and other effects on that scale. So the quantity is still an important one. Momentum, on the other hand, is a quality of moving objects. So even if something large is not moving, it still has inertia, but in order to have momentum, the object must be moving. And the faster an object is moving, the more momentum it has. The faster an object is moving, it doesn't suddenly have more mass, so it doesn't gain inertia, but it does gain momentum. And we're going to see on the next slide now the connection between momentum and force. So looking at the momentum equation, it looks very similar to another equation that we've already looked at, the second law. P equals mv, well, F equals ma. But let's just think about this for a moment. A is equal to velocity divided by time, v over t. So let's substitute. And we can see there then that m multiplied by v over t can also equally be written as mv divided by t. There's no mathematical difference. But mv, we already know, is p. And there's a lot of letters being thrown around at you there, but essentially all we're doing is rearranging the equation according to the rules of multiplication and division. And then when we get mv, we know that that's momentum, so we're putting in the letter for momentum. So we notice then that force is momentum divided by time. And what do we call it when something alters with time? If you remember, we call that a rate of change. So what that means is force is the rate of change of momentum. And now we understand something very important about the character of the relationship between force and momentum. So one of the most important principles here is the conservation of momentum, and that is that momentum is conserved in any collision, which means exactly what it sounds like. When two objects hit each other, there is the same amount of momentum after the crash as there was before it. Now, as you might imagine, this is what happens in a perfect world, but in the real world we can have energy loss and momentum loss due to other effects and external factors, but in perfect collisions this does not happen. And we're going to go on to look at a few of the basic examples of conservation of momentum. We're going to be looking at just the very simplest cases. You build up in complexity of your models by adding more and more factors in as you go. So it was alluded to in the last slide, but just in case you missed it, we should just cover what a collision is. So a collision happens when one object hits another, or when two objects hit each other. The first car hits the second car. This is a collision, and after the collision both are moving, but at a slower speed because there is now more moving mass. This may be roughly what we observe in the real world, but it isn't a perfect case. So if we look at that again, the animation from the last slide, we see a situation which is kind of realistic. It shows the sort of thing we might imagine in a crash in the real world. We see the moving car 1 give energy to car 2, which was also moving, but afterwards both cars are still actually moving. And this is known as an inelastic collision because not all the energy is transferred and some of it is actually lost. So the first of our example cases is the perfect inelastic collision, and in the perfect inelastic collision the two vehicles will stick together after the crash, and this is the case where the maximum amount of energy is lost in the system between the two cars. There has to be a reason why the cars stick together, and that reason is where the energy is lost. But momentum is still conserved. So this is called a perfectly inelastic collision. So perfectly inelastic collisions are sometimes also called sticky collisions, and here's a simple example of one here. Two 1200 kilogram cars colliding, with the second one being at rest. So if the two objects stick together like this, then they are treated as a single object with the sum of the two masses. The momentum is conserved and we calculate the velocity based on this. The new object obviously has the same momentum as the two objects had before the collision. In this case, the second object's momentum was 0, and so we have the momentum and the combined mass. We can calculate the velocity based on that. So here, if the first car had a speed of 10 meters per second, what is the momentum and what is the speed of both cars after the crash? So we can look at that, and before the collision we can say that car 1's mass was 1200 kilograms and its velocity was 10 meters per second. So the momentum is the mass times the velocity. 1200 times 10 means 12,000 kilograms meters per second. We can ignore car 2 at this point because its momentum is 0, it is at rest. After the collision, the total mass in this sticky collision was 1200 kilograms plus 1200 kilograms for a total of 2400 kilograms. And the momentum is going to be conserved, so it is still 12,000 kilogram meters per second. Therefore, if we rearrange the momentum equation, the velocity is p over m, which means it's 12,000 divided by 2400, which is equal to 5 meters per second. And you can see that those numbers divide up rather nicely. And the reason for this is because the objects have the same mass. So it's just a simple multiple of the mass, and so a simple division of the total momentum. So let's just make it a little bit more complicated, shall we? What if the second car in the last example had a mass of only 1,000 kilograms? What would the speed be after the collision? And if you've done that, try what about if the first car's speed was 15 meters per second before it hits? So, if the first type of collisions was inelastic collisions, you might imagine us to be going on to talk about elastic collisions, which we are. What is one? Here's one, and you can see that in this collision, the first car stops dead after the collision. So this is a situation in which all the energy of the first car is transferred into the second car and momentum is conserved. So if all the energy of the first car is transferred, that means the first car ends up with zero energy after the collision. And if momentum is conserved, that means that the second car will be moving with the speed the first car had before the collision. This is a perfectly elastic collision. So again, we're dealing with simple cases, and this is a perfectly elastic collision, but it's even simpler because, again, the two masses are the same. And because of this, conservation of momentum means that the two cars will simply trade velocities. They will switch velocities. If the second car is at rest when the first car hits it, then it will take on the speed of the first car, and the first car will now be at rest. We saw with the inelastic collisions, or at least you did if you did the additional example, that things get a little bit less precise when the masses are not equal, and so we're not going to look at that in this case. But the conservation of momentum principle still holds, and it's that we use to work out the velocities along with the kinetic energy. So looking at this example and noting the cars are now 1,000 kilograms, the orange car has a speed of 12 meters per second before the collision, and the blue car has a speed not of 0 this time, but of 4 meters per second. What are the respective momentums of the cars before and after the crash? So we can try and work this out again by starting off with what's going on before the collision. And this time both cars need to be calculated. Car 1 is 1,000 kilograms times 12 meters per second, giving us 12,000 kilogram meters per second. And car 2 is 1,000 kilograms times 4 meters per second, giving us 4,000 kilogram meters per second. And the total here is 16,000 kilogram meters per second. So that is the total momentum before the collision, and because this is a perfect collision, we have the same amount, 16,000 kilogram meters per second, after the collision. And we know that the total momentum is going to be the momentum of car 1 plus the momentum of car 2. And because they are still separate objects, this is not a sticky collision, that means that they have to be calculated separately and then added together. So because the masses are equal, in a perfectly elastic collision, that means the two objects will simply just trade velocities. Therefore, after the collision, the momentum of car 1 is going to be 1,000 times 4 meters per second, and the momentum of car 2 is going to be 1,000 times 12 meters per second. And they've just switched momentums, but the total momentum remains the same. And it's important to remember that although this is almost trivially simple in the way that we calculate it, we literally just swap the two velocities over, and so we swap the two momentums over because it's a perfect collision. This is just the basic case. From here you include difference of masses, you include friction, which causes energy to be lost, and a number of other effects, and everything gets more complicated from here. So you need to understand this basic form of the mathematical relationship before you move on to those more complex cases. But that's actually where we're going to leave this discussion of inertia and momentum. There's a lot more that we could do and may do after we've talked about kinetic energy, but As a basic introduction of the principles, that's all from me.